Hi again. So here's the third part pertaining to the LISA, the Local Indicators of Spatial Association. And I want to just give a little bit of perspective about how to interpret these results. So first we'll talk about some inferential issues, significance primarily, and then I close with some limitations, which are pretty much the same limitations as in any exploratory analysis. So the assessment of significance for a local statistic is actually very complex. And there's been a lot of attention to this in the literature, looking at exact versus asymptotic inference, the multiple comparison problem, which I will focus on in these sets of slides, and then the sensitivity to inference to the presence or absence of global autocorrelation, and then how much power these tests have against various types of alternatives. So if you're interested, there is a large literature there that you can delve into for technical details. I will focus primarily on the multiple comparison issue. So what does this mean? In a classical statistical setup, not a Bayesian setup, but a classical one, the test is like a unique experiment. And so the p-value associated with a test is the type 1 error of rejecting the null hypothesis when in fact it's correct. And in a local statistic, we carry out this test for each location. Now that's the rub, because in a classical case, there can be no sharing of information or data between different tests. But by the very nature of a LISA, we compute this for each location. So for each location, at least the neighbors to some extent overlap. So right there, we have a problem. This problem is encountered in many areas in applied statistics in practice, because statistics, the classical statistical framework is developed as a mathematical tool in the context of a single experiment. And now almost nobody in modern analysis does just one single experiment. In fact, in exploratory analysis, the whole nature of the game is that you try multiple approaches to see if something pops out that is interesting. And so because of that, and because we compute the statistic for each location, the classical p-value, even if computed from a permutation approach, is almost certainly incorrect. That's one thing. The second part of this issue is, of course, what is then a correct p-value? And that's much more complicated. So the literature in statistics has dealt with this issue formally, and there are a number of corrections, but these corrections, first of all, they're not actual p-values. They give you bounds on what the p-value could be. And they're Bonferroni bounds and other approaches. We'll talk about a few of these. But they don't give you an exact p-value either. So in a more recent literature where we're looking at computational inference, there is a move away from these p-values and a move away from this very strict classical interpretation of significance. And especially in our context, I would say, don't get too carried away. A pseudo p-value of 0.05 is a suggestion that something might be going on, but it's not a very strong suggestion. So I would say, as in anything, be very cautious when you interpret the results of LISA analysis. So what are some of these corrections? So Efron and Hastie have a very interesting book on inference in the computer age, so to speak, in what happens when you're, like in our case, our pseudo p-values are generated by a computational experiment. So what do you do with this? And especially in very large big data type of situations, this whole notion of significance becomes almost meaningless in some contexts. So they think a lot about that. But one notion is when you have multiple comparisons is to set some kind of target level, something that you're comfortable with as a type 1, overall type 1 error. And this is sometimes referred to as a family-wide error rate. And basically, it is the probability of making one false rejection out of a number of comparisons. And then, of course, the discussion is what should this target level be? And some people argue for a fairly high target level, like 0.1. And then you have this other literature about replicability in research and reproducibility in research, which argues for much tighter p-values. In fact, there's an article in Science that suggests instead of this classic 0.05, we should be using 0.005. And so it's not at all clear what exactly should be used. And, at first sight, it may seem incredibly confusing, and it is. So therefore, I like to use a pragmatic approach where I look at what the results are for a number of these different approaches and to what extent do they give me the same message? Do they give me the same suggestion of interesting locations? So the bounds, these are the most classic ones from mathematical statistics, Bonferroni bounds and Seedack bounds. So what is the idea here? The idea is that they basically throw up their hands and say, we cannot figure out what the exact correct p-value is, but we can set a bound that it is not going to be worse than this. And for Bonferroni, the idea is you take a target p-value and you divide it by the number of comparisons. So if you say you do 5 tests in sequence and your target p-value is 0.05, then for each test you should use 0.05 divided by 5. So that would be 0.01 for each test. And so if you do that, then the Bonferroni results guarantees that your p-value will not be worse than 0.05. So that's the idea of a bound. Seedack bounds are a similar idea, but a little more complex formula. But again, it is a correction for the number of comparisons. The problem with this approach for Lisa's is that the number of comparisons equals the number of observations. So if we take, say, the US counties, there's some 3,000, just to keep it easy, US counties, and your p-value is, your target p-value, your target alpha is 0.05, then for each individual county Lisa statistic, you should use 0.05 divided by 3,000. So as a result, nothing will be significant. So that's not very useful either. And there's been some discussion in the literature, not very large, about the idea that we should correct for the number of multiple comparisons, but it shouldn't be the number of observations. It should be something else. What is K? Should K be the number of neighbors? Should K be the overlap between the number of neighbors? And there's been some ad hoc discussions of these approaches. I would just leave it at that and look at what Bonferroni does or doesn't do, and then compare that to using fixed alpha levels like 0.01 or 0.001 and what information that gives. The drawback of Bonferroni is that very few observations will tend to be significant. So that's not that useful either. And just to illustrate this, if we use our example, and our example, n is not very large, n is only 85, so we divide the target alpha level of, say, 0.05 by 85, that gives us a de facto p-value for each location of 0.0006. And using that, we only have 3 significant locations in our cluster of low-low that we had identified before. This is for local Moran. And then if we say, okay, let's take a target alpha of 0.01, then we, in essence, only end up with one significant location, the one that we had identified earlier that was highly significant. So this is Bonferroni, basically easy. You take a target alpha level, target type 1 error, and you divide it by the number of observations. If you have a lot of observations, this is not going to work very well. Another approach, which was actually developed in reaction to Bonferroni and other such bounds, as out of dissatisfaction with that approach, is called the false discovery rate. And it's a famous article by Benjamini and Hochberg in the mid-90s, where they come up with a very practical approach. In essence, what they say, okay, let's just look at what these p-values are that we get for all these individual experiments, and then do some kind of rank size logic where we order the p-values from smallest to largest, and then we compare them to a fraction of our target alpha level, of our target type 1 error. So with Bonferroni, I is 1, n is the number of observations, and so we divide our target level by the number of observations. What the false discovery rate does, it sorts all the p-values and then creates an additional column, if you wish, of 1 over n times alpha, 2 over n times alpha, 3 over n times alpha. And as long as the p-value that we get is less than this expression, we call it significant. Now, again, this notion of significance has to be taken with a grain of salt, and that's why Efron and Hastie call it interesting, not significant. So how does that work in our example? Here's our set of results for the local Moran and all the p-values sorted in increasing order of p. And then in this FDR column, we have here the target divided by 85, 2 over 85 times the target, 3 over 85 times the target. So as long as these p-values are less than the FDR value, we count them as significant. And in our case, we see these first 3 satisfy that criterion, but here we're over. So we stop at these 3. And that's the principle of false discovery rate. It's very easy to implement. All you have to do is create this additional column and do the comparisons. In our example, for 0.05, we get a little bit more than what we got in the Bonferroni. And here for the 0.01, we basically get the Bonferroni 3 significant locations back. And so between all of these, by now we should be very wary that there is something going on in this region that is clearly not compatible with spatial randomness, pretty much no matter how you quantify the uncertainty of that decision. So that's the spirit in which I like to use these notions of significance or interestingness, if you wish, of locations. So we know our p-values are not right. It's impossible to get the right one. What do we do instead? Either bounds or this ranking with false discovery rate. And then I want to close this initial discussion of Lisa's with some caveats. As I've mentioned a number of times before, these techniques are exploratory only. They identify patterns, they identify clusters and outliers, but they don't explain them. So they suggest interesting locations, and then it's up to us to dig further and find out if we can possibly relate this pattern to an underlying process. And in that process, in that operation, we have to keep in mind the inverse problem, which we already talked about in terms of true contagion and apparent contagion, namely that different spatial processes can yield the same pattern. And what we do with these techniques is we identify clusters, but these clusters are patterns. They do not tell us anything about what the underlying process might be that might have yielded these patterns. So very important when you write up your conclusions or when you interpret your results, you don't know anything about process, but you do know about pattern. And then the other caveat is that so far, and in the last module we'll go beyond that, so far we've only treated each variable in turn in isolation. So we've only done univariate spatial autocorrelation. And the patterns that we find that show correlation among a single variable may actually be the result of interactions with other variables. So the multivariate interactions will complicate this analysis quite a bit, actually. And so then we are really looking for locations that are close in multi-attribute space and also close in geographical space. And if you recall our data cube, we could see these little data points floating in the cube that were close together in attribute space, but they were also, as it turned out, close together in geographical space, being in lower Manhattan. And then a final thing is back to the modifiable areal unit problem, is that scale mismatch. In fact, the use of the wrong scale of analysis for the type of process that we're interested in discovering ultimately can create the impression of clusters, because these clusters don't actually have a meaningful interpretation. They have more to do with scale than with anything else. And I want to close with an example of an analysis that I did some time ago of the housing market in Orange County and Los Angeles County in California in the United States. And we had very detailed data on individual housing transactions with prices, and did a house-to-house kind of spatial weights matrix and analyzed the local spatial autocorrelation, and ended up with huge clusters of high and low value, very large clusters. But upon thinking about this a little more, this was actually an artifact of carrying out the analysis at the individual house level. In a lot of the developments in the Southwest and also in the Southeast of the US, a developer moves in, takes a big plot of land, and then builds 1,000 houses that are essentially the same, one with the garage on the left, the other with the garage on the right. But if you do hedonic modeling in economics, which characterizes or relates the price of the house to its characteristics, all these characteristics are the same. And so as a result, the prices will be the same too. So what we're actually finding by working at the house scale is these larger regional scales of neighborhoods or development. So that is a suggestion where that is a case where the suggestion of clustering doesn't really have anything substantive to do, but it has to do with a mismatch of the scale of analysis. So keep that in mind when you get strange results. Think back about the MAUP. So this concludes our 3 sets of slides devoted to LISA, or Local Indicators of Spatial Association. Very important topic in my experience, the most commonly used tool in exploratory spatial data analysis. You have the local Moran, which gives you the high, low, high, low. We have the local Geary, which is a little harder to interpret, but gives a different measure of attribute similarity based on distance. And then we have the Geddes-Ord statistics, which are very similar to the local Moran, but essentially don't deal with negative spatial autocorrelation. How do we interpret these things? Very cautiously. We know that the p-values are wrong. We don't know what the correct p-values have to be, but we have ways of assessing the sensitivity of the results to choices of these p-values. And that's the key takeaway measure. Run these things, but don't stick to one particular significance map or one particular cluster map. Look at what happens as you change the p-values. Does it stay focused on the same area or does it jump around? And then learn from that. That's the main message at this point.